Hi there and welcome to the release video for our October release in 2025. My name is Christian Humbert and as usual I'd like to present the latest features of our binary level analyzers in this release for AIT, StackAnalyzer, TimeWeaver, ValueAnalyzer and TimingProfiler. There are some nice and interesting updates for this release we would like to share with you. And as usual, we would like to start with the changes and new features in the graphical user interface. The first thing is that all AbsInt tools now locally record a stack trace when there was a tool crash. I'd like to give you a short demo on this. Well, if it ever happens that our analyzer or the graphical user interface terminates unexpectedly with a crash and a segmentation fault like this, then typically a stack backtrace will be logged to the command line here. Now, if you restart the analyzer, here in this case it was an ACube4ARM instance, then this unexpected termination will be detected by the ACube crash reporter. And it allows us to inspect more details on the former crash or ignore it, of course, and start with a fresh instance of the analyzer. Well, let me now click on details in this demo. Then we will see that stack backtrace again here in this view, and we can immediately email that backtrace to our technical support by clicking on that function, or you can try to restore the recovery point and continue to work with the state before the crash. So let's try that. Click on restore. It asks me to recover from that point on and delete the report. So let's click on yes. And well, now a diff is detected between the project information in the recovery point and the project information that was referred. So let's use the information from the recovery point and store the project, give an update on the project. And well, in this case, we were lucky because the state of that workspace before the crash actually happened could be resumed, could be recovered, and we can keep on or continue to work. The new release comes with an improved create analysis experience, which means that if you create a new analysis out of an existing one, now we take over the information about the active configuration, the AIS files, and dependency info from the existing analysis. Let me give you a short demo on this. Well, in my example here, I have a stack usage analysis for the 10 millisecond task, which runs in a task-specific configuration and uses a local AIS file. When I now start the analysis and, for instance, open the call graph and decide maybe to create a separate analysis for a sub function like proc1, for instance, I can click here to open the context menu with the right mouse click and select create analysis for it. Then you see that a new create analysis dialog will appear where I can of course decide which analysis type I would like to add. In this case I want to do a separate stack analysis for the proc1, and this time now the configuration from the previous existing 10 millisecond task analysis will be taken over, and also the AIS file references. Of course you can modify them and add some additional file references if you want for this new analysis. But if I click on OK, just as it is, write this, well, you see that the active configuration and the AIS file input is taken over. The new release comes with an improvement regarding the visualization of infeasibility in the graph. In previous versions, when the execution of individual blocks or entire routines were infeasible in just a subset of all execution contexts and not all of them, and feasible in at least one execution context, well, the block or the routine was displayed as feasible. This could cause some confusion if some warning was issued during analysis that affects only a or specific execution contexts. Now, in the new version, it will be possible to show the infeasibility of blocks or entire routines for specific selected active contexts. Let me give you a demo on that. Sometimes you get warnings that some infeasible program location has been detected, or an infeasibility as an effect of a contradiction or similar, and you would like to investigate on this infeasibility in your call and control flow graph, right? You remember that some releases ago, we introduced the show in call graph and in parallel set the active context, namely that context in which the problem occurs, that can help to, let's say, restrict or filter the situations in which these problems occur. But if we go here to that program location and set the active context, we do not see in this example any infeasibility, and this is because if there is at least one context of this function in which this block is not infeasible, well, the visualization doesn't show any infeasibility. Now, in this release, we have introduced a new option when an active or a context was set to be active. This is called show feasibility for this active context. And since we set the context, the active context previously, we can now activate that additional option. And you see now that we have now the infeasibility visualized in the graph for the given set active context. And now we can start investigating on where this infeasibility is coming from. Next new feature has been requested by many of our customers. In addition to displaying relative program point offsets in the disassembly view, these can now finally also be shown in the graph representation. There's a new option for this, and I'll quickly show it how to activate it to you now. Well, the standard behavior is like this. If we analyze here the 5 millisecond TimingProfiler analysis and open the graph, well, we can see the absolute addresses for individual machine instructions here. If you switch to the disassembly, show address in disassembly, you know that you could add the, where is it, the relative offsets here. See? Well, this does not affect the graph visualization yet, but you can go to Project Preferences and switch here to Visualization and activate the Display Offsets option here. And this will permanently then change or affect the visualization. If you go back to our graph block here, we see the relative offsets now as well. As you know, the sections view allows you to visualize the row data from the executable for a given start, address, and width. And sometimes you might want to perform a reverse lookup on this row data to, for instance, check if an address in this data is associated with a symbol in the symbols table or the DWARF debug info. And this can now be triggered directly from the sections view. So in my example here, I have a constant message handler table. Well, actually, this is an array of structure elements, and every element consists of the component ID, which is an integer, and some address, namely a handler function's address. and this table starts at this address. Let me copy that information to the clipboard, and has a size of 40 bytes. So let's switch to the sections view for a moment and start looking up the content from address 60 hexadecimal here and 40 bytes of it. Well, then we see the data because it was constantly contained in the binary. The first element, the first 4 bytes, corresponds to the integer, the ID, and the next one to the handler address. So in this case, it seems the very first element here contains a null pointer. Then the next one has ID 1, and the handler target pointer has this address. Well, now we could select these 4 bytes and say right mouse click, find in symbols. This is the reverse lookup now. And if we do that, well, we end up at this symbol here. So we know we have stored an address here in this table, and this address belongs or is associated with the symbol handle progress message. Next one here in this function is probably a different handler function, namely the handle info message. All right, now we have some nice updates regarding user annotations or specifications. The first one is, and this is also, by the way, a feature that many of our customers have been asking for, that annotations which had to be bound to instruction or routine program points in previous versions of the analyzer can now finally be attached to loop routines as well. In other words, you can now take the symbolic loop name with these suffixes .l1, .l2, and so on, and attach an instruction annotation to it. Let me give you an example for it. Okay, I here have an AIT WCET analysis of our famous 1 millisecond task. I'd like to start the analysis now. And we'll see that there is an unbounded loop warning for the first loop in routine, in the start routine. Well, you can check it in the graph. The reason for that unbounded loop is that, as you can see here, we have a simple for loop. The reason here is that the message length parameter, which is a global variable, set some outside of the task, is unknown, and therefore the analyzer could not conclude with the worst case loop iteration bound. Well, except for the case, or in addition to annotating simply the loop bound, as you know it, with loop and then the name of this routine, you know, here with this loop bound annotation, of course, we could now also additionally place an enter with annotation to that loop routine. So in previous versions, we had to select a program point, an instruction program point, maybe like the start address of this basic block, and say copy AIS annotation enter with, right? And then it was the enter with annotation was tied to this instruction. Now we can simply use the symbol for the loop routine. So let's just copy it and let's go to the AIS file, maybe the global one, and we can simply say instruction, then the name, of that loop, enter with, and we could annotate the content of the message length variable. If you check the source code, you will see that it's 0x20 or 32 in decimal. Well, now if you save that and rerun the analysis, rerun it, we'll see the loop bound is automatically found now without an explicit loop bound specification. Instead, we use the enter with, which was associated with that loop routine now in the new release. The next new feature, also highly requested, our AIS editor can now handle block indentation. We have a special shortcut for it, or it can also be found in the context menu. I'll show you briefly. I think everybody knows the situation. You copy some complex text, so in this case, some complex annotation here into another project AIS file, but the, well, indentation for the scopes are missing. Well, now you can simply fix it by either marking here the block you would like to indent and use the context menu and say increase indentation. You see there's also a shortcut well, then you indent it by 1 unit here. Well, you can use, of course, here for that line the shortcut as well, Control I, and it will be fixed as well. Maybe you decide to put a try block around the entire section. Well, then again, it's easy to move everything here 1 level up again. Of course, you can also undo the indentation, and that can be done with the shortcut Control-Shift-I. So let's do that here. Remove the try block again. Well, and decrease the indentation level again. The next update on our list here affects complex areas and the annotations of them. Well, the first new thing is that you can now address members also inside anonymous unions or structures. Well, consider, for example, the following variable declaration for variable S, which is a structure containing itself an anonymous structure with components X and Y, and a union with components float A and B, and another floating variable C. Well, if you now would like to address or annotate the content of the component X inside of this anonymous structure, well, this can now be done using the area and then the complex area expression s.x, although or even there is no naming for that inlined or nested structure. Next update is on complex areas used within collect initialization directives. Well, assume we have like this structure variable S of type containing a component A of type integer, another nested structure with components X, Y, and an array contained in that inside nested structure, and another character C here. If you used a collect initialization directive and with the shortcut variable name s dot, without naming any name or component symbol, well, then it collected assignments to direct members of that variable s only. In this case, it was A and C. But assignments to the indirect or nested components X, Y, and Z were not collected using this notation. Now we are introducing the dot star complex area. That means if you now say collect initialization as dot star, it will additionally also collect values that are written to nested members X, Y, and also all array elements Z. By this release, we introduce a new addressing mode in AIS specifications to address a program point by simply navigating through the control flow graph along the taken and not taken edges, for instance, after conditional branches. I'd like to show you an example for it. Let's consider the analysis of this 5 millisecond task. Well, there is the first conditional branch here, checking the signal value, and the second conditional branch is here, where we check upon the value of the BS math index. Well, after each conditional branch, you see a green taken edge and a blue not taken edge. Now, assume you would like to annotate the block starting here, calling the BS routine, to be infeasible. Well, there are several ways to do that, but now we would like to use the new taken and not taken edge navigation through the control flow graph. Well, that means we should first go via the first taken edge, and then follow the not taken edge to receive or end up at the block calling BS. Okay, this can be annotated as follows. So I've prepared here my start of the annotation, instruction analysis start. So at the very beginning we want to start, and then we want to first follow the taken branch, the taken edge, the first one, and then the next time when we see a conditional branch, we would like to go over the not taken edge, right? And then the resulting or target block should be marked as infeasible. Okay, let's give it a try and check the call graph now. Well, we see already the effect that the BS has become infeasible, but if you have a look here, we nicely see that indeed we followed first the taken edge, then the not taken to arrive at the block here where we associated the infeasibility annotation. Additional to that, we can also say, let's annotate every block after all the not taken branches. This would be done with a star operator here. You could say not taken, all the resulting blocks after a not taken edge, we would like to comment with touched. Okay, let's see what then happens. Well, we probably see effects after each not taken edge. So let's unfold everything. So we see here a touched comment, but we also see after this conditional branch, after the not taken edge, a touched comment. And the last one here after the last conditional branch. The last but not least feature that I'd like to show today is that in a new release, the application of source code annotations can now be limited to a certain expected radius of source lines. Well, in this release, we have introduced a new within operator, especially to combine it with program point offset specifications to, well, apply an annotation only if the targeted program point can be reached within an expected source location, a radius or range. It especially makes sense to combine it with in source code annotations where you use the keyword here, like in this line 10, where you would like to annotate the next computed call from here on to resolve it with the user error handler. Now you add the within 11 here to really restrict this annotation to those computed calls, invocations that are found within the source line radius of 11. And well, as you can see in this example, it really works because we are here in line 10 with the source code annotation in this comment. And 11 lines later, we have the computed call location. Okay, this nicely works. We have a second example here in line 13 with another computed call annotation, but this time we restrict it to be applied within the radius of 3 source code lines. And since we only have that single computed call location in line 21 and nothing more, well, then you can see that within that range, no program point is found that can be applied or can be where we can resolve the computed call. So this annotation has no effect here. Okay. All right. That was everything I wanted to show today in this release video. As always, this was just a selection of the features I wanted to highlight. You can find a complete list of changes, improvements, and extensions on our website as usual. I'd like to thank you for your interest again, and I hope to see you in the next video. Thanks. Goodbye.